Looking now at doing a confidence interval question dealing with proportions, we will see that there's a lot of similarities and overlap with a confidence interval question for a mean. The one big difference is that now when we are going to construct our confidence interval, we see that a proportion question involves a z-score, as opposed to a mean question which involved a t-score. Now there are differences in what we will have to use for probabilities for that. If we think about how a t-distribution works and how the probabilities are calculated, we remember with a t-score, it's always looking at probabilities that are in the tails. And we specify whether we're doing a left-tailed test, a right-tailed test, or a two-tailed test. And with a confidence interval, it will always be a two-tailed test. With the normal distribution, it doesn't really work like that. It doesn't look at the probabilities contained within the tails of the distribution. It always looks for the probability below a certain value. So there's going to be a slight difference in the value that we have to put in for the probability for a z-score. So let's just do a quick recap on what a confidence interval is really all about. So remember, if we're calculating a confidence interval, really all it is we're trying to make an estimate for a specific population parameter. So in this section, we'll be dealing with that population parameter being the population proportion. So the main thing with these questions is we're not going to know what the population proportion is. We need to make the estimate for it. Well, if we don't know what the population value is, we can always start by taking a sample and getting the value of the equivalent sample statistic. So when we don't know the population proportion, we can start with our sample and find the sample proportion. That is the beginning of our estimate. But due to sampling error, we know that that value is not going to be exactly right. We never expect the sample proportion to be exactly reflective of the population proportion. So what we'll do for our estimate is, yes, we'll start to base our estimate on what we found in our sample, but because of the fact there is that sampling error that we can never eliminate, we're going to incorporate that into our confidence interval. And as it says, it's an interval. It's a range in possible values for the population proportion. So we take our estimate of p hat to get the low end of the interval, we subtract some error. To get the high end of the interval, we add some error. And once again, doing a confidence interval, we're not looking for a probability. We have the probability given to us. We're looking for the values associated with our cutoff points based on how much error we're allowing ourselves. So that error is going to differ whether we're dealing with a 90% confidence interval, a 95% confidence interval, or a 99% confidence interval. So if we're looking at the situation we have here, and we're dealing with a 95% confidence interval, first of all, we don't want to talk about the level of confidence itself. That's what's contained in the center of our distribution. We'll be talking about that extra little bit that's contained in the tails, or our level of significance. And if we were using a t-score, we could go and use the level of significance, because the level of significance is saying that we have a 5% chance of error in the two tails, 2.5 on the low side, 2.5 on the high side. And if we specify that we're doing a two-tailed t-distribution, it just needs to know how much of the error is contained in both those tails combined. The normal distribution, however, doesn't work that way. Remember, the way that the normal distribution works is it can only find the probability of a value and below. So if we use our high tail here as our cutoff point, what we're really talking about is what percent of the data is below this point, and that will help us find the observation associated with our high-end estimate. Now the low-end estimate will also be taken care of. If the high-end estimate has a z-score, say, of 2.5, well then the low-end cutoff point will have a z-score of negative 2.5. And that will be factored in when we go back to our formula and we have that plus minus the error in the formula itself. So if we can find the high-end z-score, it'll be the exact same value as a low-end z-score, simply negative, and again, taken into account with the fact that we have that plus minus in the formula. So if we think, what percent of our data is actually contained below this cutoff point? Well, it's the entire 95% of our confidence interval, plus that extra 2.5% in the low-end tail. So we would actually be looking up a probability of 97.5%. So again, the probability associated with this will always be from a two-tailed test. All confidence intervals will be two-tailed test, seeing as we have a low-end estimate of the interval and a high-end estimate of the interval. And with a z-score, the probability that we'll use to find that z-score will come from 1 minus our level of significance divided by 2. Or if you want to think of it another way, all of the confidence interval plus whatever probability is in that left-hand tail. And our level of significance is always, always, always 100% of our data minus our level of confidence. Once again, much like with a t-score, with a z-score, we need to be able to assume a normal distribution. And for these questions, that will generally mean that since we don't know anything about the population itself, we will need a sample size larger than 30. Looking at an example, here we have a survey of 700 consumers showing that 500 of them purchase sugar-free gum regularly. So first of all, what is a point estimate of the population proportion? Well, remember, every population parameter has a point estimate, and that point estimate is the equivalent sample statistic. So here, our point estimate for P would be P hat, and P hat, our sample proportion, not just the 500 that purchase the sugar-free gum regularly, the 500 that are purchasing the gum divided by the sample size of 700. So for P hat, we get 0.714 and all the decimals that are associated with it after that. Can we assume a normal distribution? So remember, for a question about proportion, being able to assume a normal distribution comes down to NP and NQ. Well, the issue we have with that is that we have no idea what P is. That's what we're trying to estimate. So when we don't have any population parameters to work off, we will have to sub in the equivalent sample statistics. So instead of using NP and NQ, we will use NP hat and NQ hat. So NP hat, 700 times our 0.714 and all those other decimals is the 500 successes that we found. And Q hat would simply be how many failures we have in our survey, which is 200. Yes, because of the fact that both NP hat and NQ hat are at least 5, we can assume a normal distribution. So let's go and calculate the actual confidence interval. Here we're asked to establish a 95% confidence interval for those purchasing the sugar-free gum regularly. So we know we're dealing with a confidence interval question. We ask ourselves, is it mean or proportion? Well, we're told that 500 people out of 700 people surveyed exhibit a specific trait. That is a proportion. So using our confidence interval formulas for proportions, we will need to find P hat, Q hat, Z, and N. So we've already found P hat, which if we have P hat, we definitely have Q hat. We'll leave Z alone for a minute. We know our sample size is 700. So remember, with a t-score, we could only do it within Excel. Now, with a z-score, that's not the case. We can do this question both in Excel and with the use of our standard normal tables. So let's solve this first with the standard normal tables. And if we remember what probability we're supposed to look up, remember this will be all of the confidence interval plus that bottom tail. So if our confidence interval is 95%, it's that 95% plus of the extra 5%, 2.5 of that will be in the bottom tail. So 95 plus 2.5%, we should be looking up a probability of 97.5%. Or, remember, we can always find that probability from 1 minus alpha divided by 2, in which case we get the same answer. We should be looking for a probability of 97.5%. So if we scour through the probabilities in this table, and remember, the probabilities are what's contained in the heart of the table. So we try to find the closest thing we can to 0.975. And here we can find that bang on. So that's associated with a z-score of 1.96. Well, now that we know the z-score, we can go and finish off the rest of the question. Plugging in everything we know, and again, making sure that we don't do any rounding until our final answer. We should get our point estimate of 0.714 plus or minus the error. And here we have an error of approximately 3.3%. Take our point estimate and subtract that error to get the low end of the estimate. Take that point estimate, add the error to get the high end of our estimate. And what we should find for this question is we are 95% confident that the population proportion is somewhere between 68.08% and 74.78%. Looking at the same question that we just solved by hand, and now using the Excel functions to help us solve that same question as opposed to the standard normal tables. Solving this in Excel, we will still need to know what our formula is. So here we're constructing a confidence interval. It's a confidence interval dealing with proportions. So we have the formula that P is equal to P hat plus or minus Z times the square root of P hat Q hat over N. So just like by hand, we're going to need to find all those pieces. So P hat, Q hat, N, and Z. For P hat, we have that it is the 500 successes out of our survey divided by the sample size. Q hat can always be found by 1 minus P hat. The sample size was 700. Our z-score is going to come from knowing a probability. That probability is going to have some association with the level of significance. So for this question, if we're constructing a 95% confidence interval, then we have a 5% level of significance. Z-scores will always be found with the normal distribution, but for this question, we will not be using an Excel function involving dist. Remember, those Excel functions involving dist are used to find probabilities. Here we have the probability. It's the probability associated with our cutoff points, the amount of error that we have. That's found having something to do with the 95% confidence interval. So we need to do the opposite. We have the probability, we need to use that probability to find an observation. Anytime we're doing that, we are using the inverse functions. So if we look at the normal inverse function that we used previously, norm.inv, and we look for what the inputs are, we see that this function requires not only a probability, but a mean and a standard deviation. Well, when we did this by hand, we didn't need a mean and standard deviation. We simply went to the chart, looked up the probability we were looking for, and found its associated z-score. It should be the same thing we do in Excel. So this function is actually asking of us information that we don't have. We don't have a mean, we don't have a standard deviation, and we shouldn't need it. The function that we want to use is the function norm.s.inverse. And if we look what that function requires, is the same thing that we were required to have by hand, simply the probability. All right, this function returns the inverse of the standard normal cumulative distribution. Well, that's the exact same thing we did by hand. We used our probability within our standard normal table and came up with our z-score. So the probability we use by hand should be the same probability we use in this function. And remember that probability is all of the confidence interval plus the probability contained within the bottom tail of the distribution. So 95% confidence plus half that level of significance, which would tell us 0.95 plus 0.025, we should be looking up a probability of 0.975. We can also always use the formula 1 minus alpha divided by 2, which would give us the same value, 0.975. If we hit enter, we should see a z-score very similar to what we had by hand, slightly more accurate because we don't have the same constraints of having a z-score that needs to be rounded to 2 decimals like we do by hand. And with that piece of information, we really have all we need in order to construct our confidence interval. The one last thing I like to do is to create a cell that contains the error. Now remember, if we do this, it makes constructing the confidence interval a little easier. I don't have to create this error twice, once for the low end of the interval and once for the high end of the interval. I simply make that formula once, saying that the error is equal to the z-score times, and now we need that whole thing, p hat q hat over n in a set of brackets because the whole thing is going to be square rooted. So p hat q hat over n, square root the whole thing, or to the exponent 0.5, and we should get it that our error is approximately 0.033. So now constructing our confidence interval is very simple because for the low end, we simply have to take our point estimate, p hat, minus the error, and for the high end, we only have to take our point estimate, p hat, plus the error. And what we should find is that we are 95% confident that the population proportion lies somewhere between 68.08% and 74.78%. One last thing that should be noted is that there is a definite link between confidence intervals and hypothesis testing. As we've already seen, there's a definite link between the confidence interval and the alpha value that we use for hypothesis testing. So the confidence interval plus the level of significance will always be 100% of our data. So that being said, there is a direct relationship between a two-tailed hypothesis test and the corresponding confidence interval. So if we look at a confidence interval and it contains a hypothesized value of the population parameter, then there is insufficient evidence to reject the null hypothesis. If we look at our confidence interval and it does not contain the hypothesized value of the population parameter, then there is sufficient evidence to reject the null hypothesis and instead accept the alternate hypothesis. So if we're to look at an example and see exactly what we're talking about, here we have this manager, and he claims that the average package weight is 15 kilograms. And then a 95% confidence interval was set up, and that confidence interval revealed a low end of the interval being 10.4 kilograms and 14.15 kilograms being the high end of the interval. So based on this confidence interval, is this manager's claim supported? Well, no, it is absolutely not. Since 15 kilograms lies outside of that confidence interval, there is sufficient evidence to infer that the average package weight is not 15 kilograms. What level of significance can we attach to this conclusion? Well, since it was based on a 95% confidence interval, then the level of significance is 5%. One last thing to be pointed out is something that happens when we're doing a 90% confidence interval or a 99% confidence interval by hand. So if we're dealing with a 90% confidence interval, remember the probability that we have to look up is all of the level of confidence plus half of that level of significance, the amount that is in the bottom tail. So if there's a level of significance of 10%, half of that would be 5%. So 90% confidence level plus the bottom tail 5%, we are looking up a probability of 95%. Or also we can use the formula 1 minus alpha divided by 2, where alpha again would be 10%. 1 minus alpha divided by 2 gives us the same value, 95%. So if we go to look through this table and see where 95% is, well, what you should see is that it is exactly between two values. It is right between the value 94.95% and 95.05%. Both of those are 0.05% away from what we need. So here there's really no option to choose as the closer of the two, and because it's right in between, what we're going to do is to actually split the difference of those two z-scores. So it's exactly halfway between a z-score of 1.64 and 1.65, which means we are going to use the value directly between them, which is a z-score of 1.645. The same thing would happen if we were doing a 99% confidence interval. So 99% confidence interval, 1% level of significance. Half that is 0.5%. So the 99% confidence plus 0.5%, we're looking up 0.995. And what we'll see again is that 0.995 is exactly between two different values. So what we'll use in that case is not 2.57, not 2.58, but right in between 2.575.